Good evening, ladies and gentlemen. My name is Professor Robert Saint and I'm the Pro Vice-Chancellor of Research Strategy here at the University of Adelaide. And I'd first like to acknowledge the Kaurna people, the original custodians of the Adelaide Plains and the land on which the University of Adelaide's campuses at North Terrace, The Waite, Roseworthy and Theberton are built. It's my very great pleasure to welcome you all here to tonight's Research Tuesday. This is the latest in our series of free public seminars by leading researchers at the University of Adelaide. Tonight we'll hear from someone whose research could unveil some of the universe's biggest and most tantalising mysteries. Dr. Gary Hill is an Australian Research Council Future Fellow, itself a remarkable accolade, in our School of Chemistry and Physics. He completed his honours degree here in 1988 and his PhD in 1996, working on the design study for a high-energy neutrino detector. He was then hired by the University of Wisconsin-Madison, but apparently Madison isn't cold enough in winter, so he went for a year to Antarctica, working for the University of Wisconsin, constructing and operating the Amanda high-energy neutrino detector. Moving to Madison in 1998 as a postdoctoral researcher, his analysis of that and subsequent data led to the first observation of high-energy neutrinos made when cosmic rays collide with the Earth's atmosphere. Dr. Hill spent 14 years at the University of Wisconsin working on the design, construction and data analysis of the IceCube detector. This amazing facility you are to hear about tonight occupies a cubic kilometre of ice beneath the South Pole. IceCube recently detected the first high-energy neutrinos that appear to come from the most distant regions of our galaxy or even beyond. We're very lucky he chose to return to the University of Adelaide as a future fellow, continuing his research with the IceCube detector. Would you please join me in welcoming Dr. Gary Hill?
Okay, well thank you Professor Saint for those kind words of introduction. And thank you to the University for the chance to speak to you all tonight. I want to say thanks to Maria Messer and Joe Pittman for organising the logistics of this and allowing us to be here. And especially want to thank you all for coming along tonight to hear about the IceCube detector. So what I'm going to talk to you about tonight is high-energy neutrino astronomy, which has been made possible by the construction at the South Pole of possibly the world's weirdest telescope. So this is the IceCube telescope at the South Pole. So the South Pole, as Professor Saint said, is a place where I spent a good fraction of my life over the last 15 years. And so we're going to look at the question of what's a neutrino in the first place. But before we actually get to that question, I want to just talk about what makes this telescope so weird. So we actually know it's weird because it's actually descended from another telescope that was officially the weirdest telescope ever constructed. So back in 1999, the Scientific American magazine published an article on the 7 wonders of modern astronomy. And so they listed all these different types of telescopes. They had the sharpest telescope, the biggest telescope, the farthest flung, the most extensive, the swiftest, the deadliest, not that I would know what a deadly telescope is, and the weirdest. And we thought this was absolutely hilarious because this was the Amanda detector that we were building at the South Pole. Was dubbed the weirdest telescope in the 7 wonders of modern astronomy. So in this picture we see the Amanda telescope at the South Pole. What we did is we drilled hot water holes down in the deep ice to 1,500 to 2,000 metres in the Antarctic ice cap. We deployed a lot of basketball-shaped light sensors which have things in them called photomultipliers. Now a photomultiplier works like a light bulb in reverse. So we all know a light bulb works. You put some electricity in and you get some light out. Well, the photomultiplier goes the other way. You put light in and you get electric signal out. So these are sensitive light detectors. It's also weird because it makes weird, strange pictures. It doesn't make a picture of the sky, but it captures images of events, event by event. And eventually we'll learn exactly what this is later on. This is an atmospheric neutrino coming up through the Earth and interacting with the ice outside the detector. It's also very weird. We get to dress in these nice red parkas and stand around holes in the ice. Here I am in the year 2000 supervising the team deploying one of these strings. As I said, we use a hot water drill. And around this time, when we were talking about this in conferences, people were scratching their heads and saying, neutrino astronomy? Are you kidding us? What is this about? And we said, well, yeah, we're making maps of the sky in neutrinos. And the other weird thing about this detector and this map of the sky is that's actually a map of the northern sky. And this detector is at the South Pole. And so how are we making maps of the northern sky with a detector at the South Pole? So we'll learn all about that also in this talk. Okay, the world's weirdest telescope. So what's a neutrino? So we've got to figure out what a neutrino is in the first place. Well, I just want to review what we know about the structure of matter, about what everything is made of. So we've all heard of protons, neutrons and electrons. They make up atoms, which make up us. And so here's an atom with a nucleus and some electrons orbiting the nucleus. The nucleus is made of protons and neutrons. Protons are actually made of smaller things called quarks. We don't really need to know about those tonight. We can just stop at the proton. And we also have the electrons. So this picture describes what we know about the universe, in fact, fairly well. However, in the 1930s, people were looking at the radioactive decay of nuclei, and they saw something that was very, very strange. They were watching these particles decay, and they would see electrons and protons being emitted out of these decays. And you'll notice if you add up the directions here that these don't add up. You'd expect some conservation of the energy and the momentum in these decays. And so it appears like something's actually missing. And so Professor Wolfgang Pauli came along and said, I think I know what's going on here. And he postulated a particle that eventually came to be known as the neutrino, as being the missing element that would explain what was going on in these radioactive decays. So Professor Pauli explained this by postulating the neutrino. He was also very famous for a thing that he said. I've done a terrible thing. I've invented a particle that cannot be detected. So before we talk about the detection of the neutrinos, let's just take a quick look and tie what they are and where they fit into our knowledge of the structure of matter today in the universe. So what we know today about the universe is that the universe is made of the quarks that I mentioned. So they sit in the top left-hand side of this diagram. Protons and neutrons are just made of up and down quarks. So for our daily purposes, that's all you need to know. Up and down quarks basically make everything. And there are these things called the leptons. So here's the electron that we know of, but the electron has a heavier brother called the muon, and an even heavier brother again called the tau. And each of these particles is accompanied by a thing called a neutrino. So for every electron, there's an electron-neutrino partner. For muons, there are muon neutrinos, and for taus, there are tau neutrinos. So that's the particles we'll be dealing with tonight. And what we'll see is that these particles can interact and make these, and the way we detect these particles is when they interact with something and make their corresponding partner particle. These red particles are the force carriers. The gluons basically hold the nucleus together, hold the nucleon together. The photon is ordinary light, mediates the electromagnetic force, and the Z and W bosons mediate the weak force, which was responsible for that radioactive decay that we talked about in the first place. 2 years ago, Paul Jackson gave a seminar on the discovery of the Higgs boson. And so that's basically our picture of particles in the universe. So for our purposes, we just need to worry about the leptons, the neutrinos, and their corresponding charge partners. So, sorry, Professor Pauli, the neutrino can be detected, and it was done in the 1950s. And so it was done by building a detector and placing it near a working nuclear reactor. And so what happens in a nuclear reactor is atoms collide with each other, they split, they release energy, they also release neutrinos, and lots of them. And so these neutrinos would leave the vicinity of the reactor, and they come flying actually into the core of this detector. So you can see how small this detector is. There's an arm reaching to the detector. This was built by a couple of fellows called Clyde Cowan and Fred Reines, and Fred Reines lived long enough to win the Nobel Prize for this discovery. There's a little bit of fine print in this talk, and so I'm actually, just for those who know, it was actually the anti-electron neutrino that was detected here. So all these particles have antiparticles that partner with them. We don't need to worry about that. But for all the people who know what I'm talking about, it was actually the anti-electron neutrino. It would interact and make other particles that we could see. Okay, so in terms of detecting neutrinos, neutrinos are basically invisible. They're very shy particles. They don't like to interact. To a neutrino, the world looks incredibly small. The neutrino will travel through the entire Earth, and all the particles in the Earth will look incredibly tiny, and like something running through a very sparse forest of trees, it can sneak right through without even hitting anything. Of course, if you run through a forest for long enough, eventually you'll run into a tree. And this is actually how we end up detecting neutrinos. They can penetrate through the entire Earth, but eventually they'll run into something, and they'll make something else that can be detected. So the invisible, through particle interactions, through crashing into other particles, can make the visible. And at the high energies we're talking about, all these visible particles emit a lot of light, and that's how we detect the neutrinos, through the particles they make and the light those particles produce. Okay, sources of neutrinos, they're everywhere. They're coming out of the sun, okay? If you hold up your thumb in front of your face, your thumb is about a square centimetre in area, and if you stare at your thumb for about the time I'm talking, something like 600 billion neutrinos will have passed through your thumb that have come just alone from the sun. There's a lot of them coming out of the sun. They were produced in the Big Bang, and there's about 330 neutrinos in this room, in every cubic centimetre of volume, that are just rattling around here, left over from the Big Bang. 330 per cubic centimetre. They're made in nuclear reactors. The Earth is radioactive and makes them. The human body makes them. Astronomy with neutrinos actually did start back in the 80s, but at very low energies, when a supernova explosion. So a supernova is a dying star. This star collapsed. It emitted a lot of light and heat, and it also emitted a lot of neutrinos. And so they're actually observed from this supernova, 1987A. There's about 24 neutrinos observed. And they're also made in the Earth's atmosphere. So we'll come back to this one time and time again, because our detector sits at the South Pole, and basically it looks into the heavens, it looks into the universe, and looks for neutrinos. But it basically has to look out through a sea of neutrinos that are being made in the Earth's atmosphere. Okay, so there's things called cosmic rays in the universe, which are high-energy particles that are crashing into our atmosphere all the time. Thousands, millions of them per second. They're making particle interactions that are making lots of particles in showers, and they're making neutrinos. So we're looking out through this haze of neutrinos that we have to see through in order to see the neutrinos we look for. And we'll go into some detail later on how we figured out how to do that in IceCube to make this possible. We also make neutrinos on Earth. We can make them in particle accelerators, such as the LHC at CERN, which Jack talked about 2 years ago, which has found the Higgs. You can also smash things together and make neutrinos and study them in a controlled environment. And we'll talk about the newest source of neutrinos, coming from the high-energy universe. So we now know there are high-energy neutrinos coming from somewhere in the distant universe, and our job is to figure out where and what's producing them. Okay, so I just want to talk a little bit about astronomy. So we're talking about neutrino astronomy, so it'll just help to talk about what we know about astronomy and see where this will fit in. So I was trying to think of a good definition of astronomy, and I came up with the idea that astronomy is receiving messages from the universe. The universe is talking, the universe is telling us something. So messages that come to us need messengers to carry them. One messenger for carrying information from the universe to us is ordinary light. Okay, so ordinary particles of light. The electromagnetic spectrum. Because the electromagnetic spectrum ranges from radio waves through infrared, visible, ultraviolet, X-rays, up to very high energy gamma rays. All these things are actually light. They just have very different wavelengths and very different energies. At the very, very long wavelengths, light behaves like a wave. At the very short wavelengths and high energies, light behaves more like particles. Some of us may have heard of the idea of wave-particle duality, that light can sometimes act like a particle and sometimes like a wave. Well, it's very true. Radio waves really are waves. They're oscillations of electric and magnetic fields. Gamma rays really are particles. They're just packets of photon energy. So we put the gamma rays in here. Okay, now at high energy, there are also the cosmic rays, which are charged particles coming from somewhere in the universe that hit our atmosphere. There are also the neutrinos, which we'll talk about. And there's another form of messenger at low energy, at long wavelengths, and that's gravitational waves. So there's a group working here at Adelaide on the LIGO experiment, and the idea there is to build a very sensitive detector and pick up very ripples in the fabric of space-time from cataclysmic events. Two black holes might merge and collapse, and they'll actually cause space-time to ring like a bell. And those waves will propagate out through space-time, and they'll basically make these long arms of this interferometer just change subtly in length, and we can detect these gravitational waves. Okay, so a little more on astronomy with light. So in radio, we can use, for instance, ground-based detectors like the Parkes detector in New South Wales, and we can go into space to detect other frequencies. So basically, we've got a lot of ways of doing astronomy with light. This is the Hubble Space Telescope in orbit, and this is a picture of a deep field picture from the Hubble Space Telescope. When we look out into space, we look back into time. We see the moon as it was 1 second ago, because that's how long the light took to get here. We see the sun as it was 9 minutes ago. We see the centre of the galaxy, however far away that is. We see other galaxies as they were millions of years ago, because that's how far away they were. The entire universe is something like 90 billion light years across. So we can actually see all the way back in time. We can actually split those pictures up and show where that light originated from in time. There's a lot of interesting things out in the universe for us to study. The very earliest things we can see, the most distant things we can see, this is actually an image of what we think is the earliest galaxy that we've ever seen forming, about 400 million years after the Big Bang. And this is a picture of microwave radiation left over from the Big Bang that was emitted about 400,000 years after the Big Bang. So that's the furthest things we can see with light. A lot of interesting objects out there. We'll come to talk about these a bit more later. These are things called active galaxies. Okay, so now, this is a thing called a gamma ray burst. This is a movie depiction of one of the most powerful objects we think exists in the universe. This is a dying star. And so this star can no longer support its own weight, and it's starting to collapse into a black hole. And as it's collapsing into a black hole from the inside out, it's shooting jets of matter out into space. And these high velocity jets are pushing into space, and they're crashing into gas in the interstellar medium. And we think there are actual particle acceleration going on out here. So what we think is happening is that things like cosmic rays, gamma rays, and neutrinos might be produced in these shock fronts that are forming. And so we'll see here in a minute, this thing rotates around and points at us. And we can see how this would be an incredibly bright source of gamma ray radiation, because this jet is pointing straight at the Earth when this thing went off. And so for a very short time, an object like that, this is an actual measurement, lit up the sky in gamma rays. It was the brightest thing for a short period in time in this gamma radiation. You know, it can basically outshine the entire universe for a very short period, and then it dies. Very mysterious objects, and we'd like to know more about what they are and what powers them. So we put satellites into space also to study high-energy gamma rays, high-energy particles of light. The Fermi satellite is orbiting the Earth, and this is a map of the sky made in these very high-energy gamma ray particles of light. We can look for gamma rays on the ground as well. So these gamma ray particles are so energetic, we can use the atmosphere as a detector. The atmosphere makes a big shower of other particles, and the gamma ray crashes into the atmosphere. It splits and dumps energy into all sorts of other particles. And we can put telescopes on the ground and measure that light and measure those gamma rays on the ground. That's an experiment called HESS in Namibia, which Adelaide University is also involved in. And so with that, we can make maps of the gamma ray sky. This is a map of our galaxy. So the centre of the galaxy is here. You can see there's many, many active regions of high-energy particle emission in our own galaxy. These are all possible candidate sites for making the cosmic rays we talked about, and also for making neutrinos. And so there's a lot of places we can go and look, because nature's given us a lot of clues on some of the areas we can go and look. Okay, so now I come to cosmic rays. In a moment we'll see how cosmic rays, gamma rays and neutrinos all fit together in one puzzle. So cosmic rays were really discovered in the early part of last century. A fellow named Victor Hess hopped into a balloon, he took some instruments up in a balloon, and he measured the ionising radiation in the atmosphere. And what he found is that it got higher as it went higher up, and he was actually measuring showers of particles being made in the atmosphere from these cosmic rays. We can actually plot what we call a spectrum of them. And so this is a picture that shows measurements of cosmic rays arriving at the Earth. This is the energy, and this is basically the number of events that are arriving per energy. So at low energy, there's a lot of cosmic rays coming to the Earth. At the highest energies, there's very few cosmic rays, something like 1 per square kilometre per century arriving at the Earth. So we need very big detectors to detect these things, and all sorts of things in between. We think they're mostly protons and even heavier nuclei like helium, other nuclei all the way up to iron. So somehow nature is throwing these particles out into space, and they're coming to meet us. How we detect them, and this is important for neutrinos later on, is that a cosmic ray will hit the Earth's atmosphere and make a shower of particles. And within those showers of particles, we can detect them on the ground and measure the properties of the shower. And they also make very penetrating particles. They make neutrinos, they make the things we call muons. So cosmic rays provide us with showers of particles in the atmosphere, and they're making our background neutrinos that we're going to have to look out through to see the cosmic neutrinos. This depicts how cosmic ray shower detection works on Earth. Again, we can look at the shower coming in the atmosphere, all these high-energy particles, and we can look at the light being emitted by it with a telescope, or we can lay out a big array of detectors on the ground, and just measure the particles as they cross over this large area, you get these huge pancakes of particles and light hitting the ground that you can measure with these large telescopes. One such telescope is the Pierre Auger Observatory, which is in Argentina, and Adelaide Group is one of the founding members of Pierre Auger and very, very important in that collaboration. So that depicts the detector, the Auger detector in Argentina. Okay, so we can do astronomy with cosmic rays too. So these high energy particles are coming from space, so they are messengers bringing messages to us. And so these black dots show the arrival directions of the very, very, very highest energy particles we've ever seen. They show the directions they came from in the sky to us. The blue dots show possible sources they could have come from. And so you can do a statistical exercise to try and see whether the black dots line up with the blue dots at a greater rate than you'd expect by chance. And so from analysing these cosmic ray arrival directions, we think it's possible that some of these particles have travelled from these active galaxies and come to Earth and have been detected. We know the active galaxies are there because we've measured them in radio and optical and gamma ray, for instance, so we know where to look, and so we know how to try and line these things up. So there's some evidence that cosmic rays might be coming from these high energy objects, but we'd like to know whether that was really the case, and neutrinos can help with that. So we'd like to know, what these are, where do they come from, these highest energy particles, and importantly, we'd like to know how did those particles get so much energy. So how much energy? Okay, if anybody's played cricket, you're familiar with a fast cricket ball, which will be going about 100 miles per hour. So a cricket ball weighs 156 grams. So you can calculate the kinetic energy contained in that fast cricket ball that Jeff Thompson was hurling at the West Indians in the 70s. And that amount of kinetic energy comes out to a measure of about 10 joules. A joule is just a measurement of energy, a unit of energy. So how much energy is 10 joules? Well, it actually can pack a lot of punch. And I know that because I've been struck in the head by a bouncer that I tried to duck and weave and it got me. So I know that 10 joules can pack a lot of punch. Well, what we know also is these highest energy cosmic rays, they contain something like 10 joules in a single elementary particle. Okay, that is a phenomenal amount of energy to be put into a single elementary particle like a proton. And the question is, how do you make a proton get that much energy? You can't just give a proton to a fast bowler and have them try to accelerate it because they can't move their arm fast enough to do so. So how hard is it to actually make particles of that energy? Well, we accelerate particles on Earth. We do that at the LHC. So Jack talked about the LHC 2 years ago. I've stolen one of Jack's slides. Thank you, Jack, for that. And so this is the Large Hadron Collider in Geneva, Switzerland. And so this is a 27-kilometre ring near Geneva Airport in which we are accelerating protons, accelerating these particles to high energies. There are two main detectors in the beam. There's CMS and Atlas that measure the collisions of the particles and see what come out. But the point I'm trying to make here, that this is really complicated. This is hard stuff to try and accelerate particles. You have to use magnets in order to confine them, to keep them in the beam, in order so they can get a kick every time they come around and get another boost in energy every time they cross past the boost point. These things are accelerated up to nearly the speed of light, travelling this 27-kilometre ring. The machine is full of superconducting and superfluid liquid helium. I don't even know what that means, but it's down near absolute zero. It's even colder than interstellar space. The beam pipe is under a vacuum better than outer space. And these violent collisions produce temperatures that were experienced way back near the Big Bang. The point I'm trying to make is it takes a lot of work and a lot of effort. It's very technologically difficult to accelerate particles to the energies you do in the LHC. But we can compare what we can do on Earth to what nature is doing. So I've indicated on this plot the energies we get up to at the LHC. So in physicist units of energy, we talk in electron volts. The next run of the LHC will get a beam energy of about 14 TeV. Nature is accelerating these particles up to about 10 to the power 20 electron volts. Okay, they're different units, but all you need to know is that this energy is something like 1,000,000 times higher than that energy. Okay? So the LHC has done this wonderful job of getting particles up to 1/1,000,000th of the energy that nature is doing out there somewhere for us. And we'd like to understand how nature does that. Okay, so now we come to neutrinos. So how can neutrinos help us out in this picture? Well, neutrinos can help sort of tie together cosmic rays and gamma rays and help us understand the origins of cosmic rays and the origin of gamma rays. So how can they do that? Well, this is an object, a depiction of an object that's called a quasar. So you may have heard of a quasar in the past. These are some extremely bright objects that were seen way off in the distant universe. It wasn't known how far away they were initially, but then we measured how far away they were and realised just how energetic they had to be. Phenomenally energetic objects. We think they're powered by black holes. So Einstein gave us general relativity, which gave us black holes. So we think a quasar has a huge black hole at the centre, and the quasar is gobbling up other suns and gas and dust in its vicinity. And black holes are actually very efficient engines. You might think a black hole, which is something from which nothing can ever escape, would just swallow anything up. But as that stuff falls into the black hole, all that gravitational energy gets converted into kinetic energy and heat energy, and you actually liberate a lot of the rest mass energy, all that gas and dust. They're actually very efficient engines at producing energy. And they also produce jets. So we saw some jets before in our gamma ray burst. So an AGN, with its spiralling accretion disk into the black hole, will produce jets. And we think in this might be where nature has built its own Large Hadron Colliders in some form in the jets. And we'll talk about how that might be working. Okay, so how might that work? How might nature accelerate particles? So we knew that to accelerate a particle at LHC, we needed magnets to basically confine the particle such that you could keep accelerating it. So nature's going to need some magnetism somewhere in it. And nature's also going to need a way to add energy. And if you remember the picture of my GRB, we saw that the particles streaming out into the interstellar medium, they basically hit the medium out here. They created what's called a shock. Okay, you don't really need to know what the details of a shock means. All you need to know is that we think that when particles go back and forth across one of these shocks, as we call it, they gain energy. So what we think is happening in these jets, there is some kind of shock in this jet, and what we think will happen is that a particle will rattle back and forth across the shock, confined by bouncing back and forth off some magnetised clouds that keeps it there, so it can bounce back and forth and gain energy. Some of them will escape, and you notice this guy gained some energy and then disappeared off. That's how we think a cosmic ray gets made and accelerated to these extreme energies. That's not the fate of every proton in one of these jets. There's light in the vicinity, there's radiation. So what can happen other times is a proton can get accelerated, it can hit the photon and make another particle. So that moved away too quick to see what it was, but I'll tell you that was a gamma ray that made in that collision. And finally, another proton down here is going to accelerate. It's going to hit this photon and it's going to make something else. That was a neutrino. So we think in these active galaxy jets, we think we're accelerating cosmic rays to these high energies, and we think we're also making gamma rays that we've observed and neutrinos, which up until recently we had not observed. And so we think these types of environments are where these things are happening. So it's important for us to study neutrinos because if we can measure neutrinos coming from one of these objects, it's another way of gaining information about what might be going on in these objects. So that's the connection between the cosmic rays that we've measured, the gamma rays we've measured, and the neutrinos that we want to measure. The neutrinos can tell us about what might be going on in these objects. Now, once they leave these objects and come to Earth, if the object is close enough to Earth, and I'm talking in parts of our distant galaxy or even a nearby other galaxy, the particles can make it all the way to Earth. The neutrinos will always travel in straight lines, so will the gamma rays. And if the protons are energetic enough, they can also travel to Earth in a straight line. The thing is that protons are affected by magnetic fields. So the magnetic fields bend them around at the LHC. They also bend them around out in space. And so a proton has got to be very energetic to do astronomy with it. It's got to be energetic enough to pierce through the magnetic fields and not be bent. But if it's less energetic or if the magnetic field is stronger, the proton can actually get bent and we can't actually tell where it came from. So now we've got an object further away, we've got some strong magnetic fields out here in the universe, and what happens is the proton is spinning in the magnetic fields, and when it arrives at Earth, we lost all information about where it came from. Okay, so it can be sometimes hard to do astronomy with protons. If they're very energetic, we can. If they're not, they get all wobbled around, and they really come at us in random directions. Again, the neutrino makes it here completely unaffected. I hope you're starting to get the idea why I like the neutrino. So one final case, imagine an active galaxy that's even further away, So here we're talking a few 100 million light years. So a light year is the distance light travels in 1 year. That's how we measure distance. This is a long way away, but on the scale of the universe it's actually pretty nearby. So from that distance, we start to see that photons will actually not make it. They'll get absorbed. They'll run into other photons and disappear. Same will happen with protons. They'll travel about that distance, but they'll collide with other photons and disappear. But again, the neutrino just sails clean through the universe. So I told you the neutrinos are very shy. And so the neutrinos basically travel through the whole universe. We can see them from everywhere. These other particles, we're limited in the range from which we can see them. How do we detect a neutrino once it arrives at Earth? Okay, you need to, because the neutrino is a very shy particle, you have to wait a while for it to actually interact and make something you can see. And so you need to build really big detectors. So remember, the first detector was about so big, but they were detecting neutrinos coming from the nuclear reactor, and there was just billions of those. And so you only needed the odd 1 in a billion to interact, and you could see them. We're talking about extremely low levels of neutrinos coming from these distant objects, so we need really big detectors. And in fact, we need about a kilometre scale detector, and so we need something that's about a kilometre across. And the way it works is the muon neutrino comes in, it interacts in water or ice, and it makes its partner the muon. And this particle is invisible, that particle is visible, and so we can see light emitted, and we can measure the arrival direction of that muon particle. And so we can do astronomy. We can tell the direction the muon came from. We know that this basically preserves the direction, so we can indirectly detect the neutrinos. So we're doing what we call indirect detection. So neutrinos arrive to the Earth, they make other particles we can see, we detect those other particles, we see where they're coming from in the sky, and say, okay, that's the directions the neutrinos came from. The blue light is actually the glow you see in the core of a nuclear reactor. It's called Cherenkov radiation. And this is actually a visualization of how this particle detection works. This is a simulation, so we use computers to understand our detector. This is a muon moving through the IceCube detector. As it's moving through, it's emitting light. You can see this sort of cone-shaped shockwave of light it's emitting. And every one of these lines is a path that an individual particle of light took as it left. You notice that they don't go in real straight lines towards the end. That's because the ice has dust in it at the South Pole. And so the photons are travelling a certain distance and they'll get scattered off some dust and they'll change their direction. But there's enough information in all those photons leaving that muon for us to tell the track that particle made through the detector. We can tell to much better than a degree where those particles came from. So we're getting to the point where we can do astronomy. The other type of neutrino, and these are the ones that we've really made the detection with, are the electron neutrinos. So the muon neutrinos make muons, which make tracks. The electron neutrinos crash into the detector and they make electrons. Now electrons are very light, they don't travel very far, they lose their energy very quickly, and they lose it in a very short cascade of other particles which make light. So here again, we're seeing the emission of light from the electron made by the neutrino, and the light diffuses through the detector. We can measure it, we can measure the energy of the particle, we can measure the direction the particle came from. You see the colours aren't symmetric back and forward, there's different colours. There's enough information in the pattern of that light that we can tell where those little spherical blobs came from. We can tell to about 10 degrees in the sky where those little spherical blobs came from. Okay, so let's talk about some history of constructing neutrino detectors, and then we'll get on to our discovery. So the first idea was the Dooman collaboration in Hawaii. It's my friend Professor John Leonard, who actually examined my PhD thesis when it was submitted for examination. I gave a talk out there last November and he was very pleased to hear about our discovery since he's one of the pioneers of this field. So they were building these sensitive light detectors and they were lowering them into the deep ocean off Hawaii, off of a ship. And so it's a very good idea. In some ways I would have rather worked in Hawaii than at the South Pole. But unfortunately it's very difficult just logistically to do this in the deep ocean. And so unfortunately their valiant efforts to do this and all their pioneering efforts failed. But at the same time other groups were trying out the same idea. One other group trying the same idea was actually us here in Adelaide. So as Professor Saint said, I cut my teeth working on the design of a neutrino detector. And this is Roger Clay, who was one of my supervisors, along with Professor Bruce Dawson. And when I was wanting to do a PhD, Roger said to me, I've got this idea for this thing I want to try and build. And I said, what is it, Roger? He said, well, I think I want to cover up a lake with black plastic and try and keep it light tight and detect neutrinos. And I said, fantastic, when do we start? So anyway, so along with Roger and along with Janice Reid, who was a fellow graduate student at the time, we spent many a long night out on the Blue Lake. So we built instruments in order to try and measure how clean the Blue Lake was. And we built instruments to try and measure those muon particles coming down through the atmosphere from the cosmic air showers to see if we could actually do particle detection in the lake. Things didn't always go well. You can see Janice hunkering over a little laptop here trying to debug some problem with one of the detectors. Roger's looking on, giving his best advice. And you can see me here puzzling over why one of the water clarity detectors isn't working. Mostly things leaked. Mostly water just got into everything. But we had a lot of fun down at the Blue Lake and really cut our teeth on neutrino astronomy in the Blue Lake. So eventually I got a job, as said, with the University of Wisconsin in Madison. I went to the South Pole. That's my first picture of the South Pole on the plane going in. That's as I was one of the first people off the plane, so I took a shot back of the others getting off. I lived underground for a year under this dome with these buildings, and it was a very, very fun time. I claimed the pole back for Australia, down there now. These days I can't do that because I'm a dual citizen of the US, so I have to respect both flags now. But back in those days, it was Australia's, as far as I was concerned. So as I said, we built Amanda. So we built this prototype detector down there, which actually worked. We actually found neutrinos coming through the Earth. So we actually proved that we could actually do this. A lot of people said, you can't do this, it will never work. And we proved that we could do it, and we started neutrino astronomy. So as I said, we constructed this thing over these 5 years. I spent 3 seasons down there, including my winter, doing this. We drilled hot water holes into the ice with this hot water drill. We put these modules in. We used to autograph them a lot. This was Happy New Year 2000. We were deploying a string on midnight of 1999. So we actually had a break for some champagne at midnight, a bit of a celebration at the pole. So the way you work at the pole, you heat up hot water and use hot water to melt holes down into the ice. So this was the drilling camp at that time. There I am with another Australian, Darren Schneider, who came down as a winter over for us as well. And so my job on ice was to lead the team that was putting the detectors into the ice. So I did that for Amanda, and I've done that for IceCube as well. So I know a lot about attaching things to cables and plugging them in and getting them down into the ice safely and building these detectors. So there's one of the modules going down the hole. All right, so now I want to talk about how we look out through the sea of atmospheric neutrinos. So the cosmic rays are filling our atmosphere with neutrinos. We have to look out, we have to eliminate those. So I'm going to tell you about how we do that and how we've discovered the astrophysical neutrinos. Okay, so the cosmic rays hit the Earth's atmosphere. They make big showers of particles. So all I care about out of this shower is the muons that get made. Okay, the muons are the particles we can see. And I care about the electron neutrinos that get made. And I care about the muon neutrinos that get made. Lots of other things in here. This is all we're going to care about, is what happens. So I'm taking this picture of a cosmic ray hitting the atmosphere, and now I've actually replicated the same situation around the Earth. So here's IceCube at the South Pole. Okay, so IceCube's buried under the ice at the South Pole, and it's looking for neutrinos from all directions. So here's a cosmic ray that made some neutrinos and a muon. The muon didn't make it very far into the Earth. See, the muons, they like to lose energy, and so they only travel maybe 1 through 10 through 20 kilometres. So they don't make it all the way through the Earth. Neutrinos, on the other hand, very shy particles. They travel through the whole Earth. Some of them we can detect. So you see this picture repeats all around the Earth. The neutrinos get through the Earth, and the muons do not. Okay, so the muons get stopped 10 kilometres in, and most of the neutrinos make it in. So we're looking down into the Earth, and we're looking for these neutrinos. And these muon particles, we don't worry about them. If we think what happens above our heads at the South Pole, we have the same thing happening. But the difference is that the muon particles, the noisy muon particles that like to make lots of light in the detector, they do come into the detector from above, okay? And they're very hard to reject. Now the key thing is, when we look above our heads at the South Pole with IceCube, there's billions of muons coming through here for every neutrino we expect. So it's a very huge background of particles we have to look out through. And so here's our signal neutrinos coming from deep space. See, I put a little label on there. I put a little active galaxy there just to label those for you. So we've got the good ones we want to see, and we've got the background ones we want to get rid of. So then some of those are coming in from objects in deep space from above. Okay, so now we split it in two, conceptually. And so what we see coming up we see just neutrinos. We see neutrinos made in our atmosphere. We see neutrinos made in distant galaxies. There's a very few ones from distant galaxies. There's a lot in the atmosphere, so they're a big background. Coming down, we see millions and millions of these muons in our detector for every neutrino we expect. Now, there's a scientific term for a situation like that. It's called the too hard basket, okay? And so initially, we put all that in the too hard basket and said, forget it, we're not going to be able to pick out neutrinos from above our heads. There's too many background particles. But it turns out that's actually how we discovered them, and I'll tell you in a moment how that worked, because it's actually very clever. So we went and spent a long time at the South Pole doing astronomy by looking down into the Earth, with our heads down, looking down into the Earth. We were basically looking for neutrinos coming from the deep space on top of a background of atmospheric neutrinos. So there's lots of atmospheric neutrinos, but they tend to have fairly low energy. There's very few neutrinos coming from the distant universe, but they tend to have higher energy. So what we basically look for, we measure the energy of all the neutrinos we see, and we try and see if there are more neutrinos at high energy than we expect. And we look for basically a bump in the tail. We can also see where they're coming from in the sky, and because maybe there's a bright source of neutrinos out in the universe. Maybe there's a source of neutrinos that's so bright that it doesn't matter, and we'll just see lots and lots of those all coming from one place, and it won't matter how many atmospheric neutrinos there are. Anyway, we toiled away with Amanda for a lot of years. We didn't see any of this. We saw the atmospheric neutrinos. They were uniformly spread across the sky, but we knew we had to build a bigger detector, and that was IceCube. Okay, so this is the IceCube collaboration. It's a collaboration of about 40 institutions around the world, now including the University of Adelaide. So here's our group in Adelaide. There's Alex and Rebecca, who are honours and MPhil students. Mark is a PhD student. Ben is the postdoc, who actually helped me clean up this talk a lot this afternoon, so thank you very much for that, Ben. Sally is a master's student, and there's myself. And also Bruce Dawson and Ray Prothero sort of pay attention to what's going on with our work in co-supervision. So we constructed IceCube over 7 construction years. We put all these modules down into the ice. We carried lots and lots of cargo and fuel to the South Pole on Hercules aircraft. This is the station at the South Pole. It's all funded by the National Science Foundation in the United States. This is the South Pole station at night time and with the auroras. Hot water drilling. So we've advanced with IceCube in how we drill holes into the ice. We've got much better at it. This is the drill camp in the final season. You can see a couple of people standing there. Lots of hoses around the drill camp. This is the drill. And so this is a schematic of how we drill hot water holes. So here you see there's an initial drill, which is basically just a hot poker that makes an initial hole in the ice. And then we take that one out and we put in the hot water drill, and that basically shoots a jet of hot water down into the ice and melts its way down to about 2,500 metres. So we drilled 86 holes. We put nearly 5,000 of these optical sensors into the detector. So just a few more pictures, I'll just skip through quickly. These are the modules waiting to be attached to the string, being attached to the string, driving the winch. There's the cable for one of the strings, attachments, and then going down the hole. 5,000 of those went into the ice. Here's some pictures of us after some string deployments. Big lot of computers in this building to analyse all these data. Okay, so now let's talk about how we actually managed to discover the extraterrestrial neutrinos. So again, just to remind ourselves, here's the picture of the cosmic ray showers making the atmospheric neutrinos, making these particles, the good ones, the signals we want to see, the backgrounds we want to reject. So something a couple of years ago made us reassess the too hard basket. Okay, first off, this is just a picture of an atmospheric neutrino coming up through the detector. So this guy's propagated through the Earth. It's made a muon, which we detected coming up through the detector. This is an event coming down from the atmosphere. It's lit up detectors at the surface, and then you see particles have travelled down into the detector. So these are the sort of backgrounds we want to get rid of coming down. We want to look at the things going up. So we toiled away for a long time with IceCube, looking down into the Earth, like I talked about. We were getting to the point where we said, well, if we don't see something soon, we never will, because we could calculate our sensitivity. And so something happened in 2012 that made us rethink this idea of the too hard basket. And what happened was we saw 2 very bright neutrino events interacting in the detector coming from above our heads. We can measure the directions of these. We know they were coming down, and they're just these explosions in the middle of the detector. They're electron neutrinos. So now, here's the key point of the talk. It's how we get rid of, how we look up into our unassailable background. Okay, so this is how we do it. So we know that if those particles had come from outer space into the detector and made that pattern, it would have looked like that. So that's a particle that came from a distant object in the universe. Now, suppose that was made by a cosmic ray in the atmosphere. What would happen is that particle, the electron neutrino, would make a similar sort of pattern to this. They look the same so far, okay? So you can't really tell them apart. But notice there's a muon there. So all these showers make muons when they make these neutrinos. And so this muon, remember, it's the noisy particle that makes a lot of light as it goes through the detector, and it gives itself away. It gives away the whole game. So these neutrinos from the atmosphere, they can't sneak into the detector because there's always a muon that's running along with them advertising they're there. It's like walking into a party, you're very quiet, you're trying to stay out of trouble, but you've got a very drunken friend who's with you, and that drunken friend gives away the fact you walked into the party. And so basically, we can reject these neutrinos made in our atmosphere and just look for the ones coming from the distant universe, and that's what we think we've seen. So those get rejected in our analysis. We keep all of these, so now we're looking up into the unassailable background and throwing it away very easily. So we keep those. This is the highest energy one we've ever seen. It's a 2 PeV neutrino, and I hope it will start. There it is. That shows a picture of what the highest energy neutrino ever observed looks like in our detector. It's huge. I mean, that's hundreds of metres across, the size of that explosion in the detector. These are gigantic images that we're making of these events. So knowing now how to look up into the southern sky, we saw a lot more of them. So here we are, there's another 12 of them we saw. We saw the new 2 PeV one. We even saw some muon tracks actually start in the detector. So suddenly we've got a lot of events we can play with. And so we're looking up into the sky and seeing wonderful things. We wrote a paper about it. We made the cover of Science back last November. And we did some physics analysis. And so what we did, we looked at the energies of the events compared to the directions they came from. We did some complicated statistical analysis on it, and you'll see a thing here, 5.7 sigma rejection of atmospheric only hypothesis. It basically means that if you figured out what our signals we saw would look like if they were made in the atmosphere, it's very improbable that happened. So we really know that these things must have come from outside the atmosphere. This shows the energy spectrum of the particles. Here's the very high energy ones, and you can see there's no backgrounds at all expected out here. Very clear evidence of a signal in this analysis. We've also still been looking down into the Earth, and so now that we've made the discovery from above, we now realise we can see it also from below. We can see things coming up, and so now we can actually see them coming up as well. So this is the atmospheric neutrinos tailing off at high energy. This is a prediction for the astrophysical ones, and we can see that we're actually now seeing them also coming from below. Okay, so astronomy, the final point. Looking into the sky, where are they coming from in the sky? All right, so this is a map of the sky. And so the question is, do these things cluster? Is there a bright source in the sky? Well, if you have a look at that, you might go, well, yeah, there is, okay? Seems to be a lot of events coming from one point in the sky. Humans are good at seeing patterns, and often those patterns are coincidences. And so we can illustrate that basically by looking into this audience and looking for coincidences. So are there any neutrinos in the audience? Yep. It's a bunch of guys sitting back up there wearing neutrinos on their T-shirts, which is my group. Now, you know that didn't happen by random chance, okay? That happened because I told them to do that. But if we wanted to check how often that would happen by random chance, what we could do is just have those guys come into the lecture theatre and put them down randomly in different places and see how often they accidentally sit in the same place. We can do that many times over and over, and we can assess how probable some sort of pattern is in our data. You guys can sit down now, thanks. So anyway, so last week Ben actually did this exercise for me. He said, this is the real sky we see. This is a measure of how clustered up those events are in the real sky. So what he did, he generated thousands of random skies. He randomised this over and over and over and over and over again, and he generated a lot of random skies. And he gave me some examples of the random skies that look less clustered than one we did see. So here's random skies that look less clustered than our real data. That happens 93% of the time, okay? Then he showed me plots of random skies that look more clustered. So these are more clustered skies than what we saw. Okay? So you can tell that this must happen 7% of the time, 100 minus 93. So in our language of statistics, that's actually not a very small probability. We would not come out and say, with a 7% random chance, we're going to stake our credibility and say there's a source in that spot in the sky. We need more data to confirm that. We really want to get down to numbers here that look more like 10 to the minus 6, 10 to the minus 7. We want to be really, really certain about that. But that's basically how we look for randomness and try and tell whether things are random. So the answer to our question is, well, it's about 7% chance that you'd see something like that just by chance. That's a pretty big number. And so our statement is the clustering we see is consistent with random chance. We really don't need to suppose there's a clustering of neutrinos right there to explain this. We can also look at, remember we talked about a lot of gamma ray sources, possible places where neutrinos come from. We can also try and see if our events actually line up with these black dots and overlap with those black dots. They don't really. Again, it just looks consistent with random chance. Remember, the galactic plane was a big source of gamma rays. So this is now in galactic coordinates. That's the plane of the galaxy. And it sort of looks like there's events near the plane of the galaxy. There's sort of a 2.8% chance you'd produce that pattern by random accident. But again, that's too big a number for us to say we think they're coming from the galaxy. They may well be. But some of them here are certainly coming from other galaxies, because this is outside the galaxy where these are coming from. So again, we make a very consistent, careful statement, again, consistent with random chance. So we need better methods of analysing it, we need to take more data. So here in Adelaide, we're working on better methods. We're working on better methods of analysing these sky maps, working on better methods of telling the directions and measuring the energies, because these are the key things that we need. So we're very active in the collaboration in improving these analyses. We need better methods, we need more data. So the detector will run for 15 years, it will take more data. And also we have plans to build a bigger detector. So remember we went from Amanda to IceCube, so we want to go to something even bigger. So in the US, we're proposing to put in another 100 strings. And I look at that and I go, oh my gosh, I did 86 already. I spent 7 years of my life there. It's going to be a lot more summers I'm going to spend at the South Pole building this thing. So we have plans to build a bigger detector. And so finally, in summary, we've built the world's weirdest telescope. I hope I've convinced you of that. This is a very strange thing. We've measured high-energy neutrinos, and we're pretty certain these things have come from beyond the Earth. They've come from our galaxy, they've come from distant galaxies. We want to know where they come from. We've started to do astronomy. So there's our first picture of the sky. That's our first map of the sky in neutrinos. This is high-energy neutrino astronomy. So, and hopefully this will yield many surprises and will be the start of many wonderful discoveries for years to come. So thank you very much for your attention.
Gary's agreed to take some questions, if anyone has a question for Gary.
You've got one up in the middle. Thank you.
Gary, that was interesting and fascinating, thank you. Especially as the first definition of neutrino I heard was nothing spinning. So how you spend your life studying nothing. Surprise.
Yeah, it's about the closest thing to nothing you can get. They do weigh something. They don't weigh nothing. You know they weigh something, but it's not much to them.
But the question's totally away from the neutrinos, more about the detector. Mm-hmm. What do you actually do with the hulls once you've inserted the detectors? Do you fill them back up with water to freeze again?
No, we don't need to fill them, because what the drill does, it actually just melts the water. And so there's actually a column of water that's sitting there. And so the drill is moving down through the ice and it's melting more and more water, and that water just sits behind there. In fact, we are pumping the water out to recirculate it back through the drill system. Mm-hmm. So the holes stay full of water. We can look down from the surface and see the surface of the water down at about 70 metres below the soft fern layer. So basically the instruments go in when the hole is liquid, and we have about 24 to 36 hours before the hole starts to freeze back, before we can no longer get them in. So my task was to make sure we got these things into the ice safely in that window when the hole was liquid, So they go in and then they freeze in, and that couples them optically into the ice. So the water stays there.
Okay, so presumably then you can't recover them if something goes wrong.
No.
They're there permanently.
No, they're permanently there. The glacial ice is moving at about 10 metres per year, and so that gives it about a lifetime, about 100,000 years before that part of the ice pack drops off into the sea. And then we'll finally have the ocean detector.
Just one final question. What is
we do have ocean detectors now, so that has worked.
What's the temperature in the ice, and does it vary from surface down to the bottom?
Yeah, it's colder at the surface. It gets a bit warmer as you go down. That's actually good, because if these detectors, they like to operate cold. So those photomultiplier devices, they operate best when they're cool. So the noise rates in these things are incredibly low. There's just random noise around in the ice, but the PMTs themselves are very cool, and so the random noise in them is very, very low, and that's another advantage we have of being in ice.
From what I can gather, neutrinos don't seem to be affected by gravity. Would that be true?
No, they are. They would bend in, gravitational distortions in space-time. Yes, they'll follow those.
How could you be absolutely certain with some of the more distant ones where they come from then, if they could be slingshotted as such around black holes or other?
That effect wouldn't be very strong. Gravitational lensing effects in light aren't that strong. We can see light, proper images from clear across the universe, and we expect it will be the same with neutrinos. Gravitational lensing is where light from an object in the distance is travelling past something between us and it, and as that light travels around that object, it gets bent, and so it gets bent a little and it arrives at us here, and it makes fake images around there. That's what gravitational lensing is. So I guess that would happen for neutrinos, but the thing is that effect would be so tiny compared to our ability to tell the direction of the neutrino, we would never be affected by that.
Okay, thank you.
Have you progressed to the point where you're able to determine how well the detector may assist in determining the presence of gravity waves?
Oh no, we can't do gravitational waves with this thing, no. No, you need very, very precision instruments where you have light beams bouncing back and forth between mirrors. That's a totally different type of detector. We're just a clunky old high energy particle detector. Particles come in, they blow up, they make light, we see it. Detecting gravitational waves, they ripple in space-time, that's really, really hard stuff. You can talk to some of the people here that do that at Adelaide. That's very high precision work. It's not something we can do.
We've got one more question, and we'll make that the last question, I think.
Just because sources aren't in the plane of the galaxy doesn't mean they aren't in the galaxy. So how certain are you that some of the sources are outside the galaxy?
Yeah, the number of sources is pretty much, correlated when you look out into the galactic plane. The galaxy is fairly flat in its disk. Okay, but you are right. It doesn't the source, there could be a source that sits above the galactic plane that is part of our galaxy. But if you think about, what the concentration of stuff is in the actual sort of flat galaxy itself compared to above and below it, I really think if we're seeing things that are not pointing at the galactic plane, that they're coming from other galaxies.
Okay, thank you, Gary. It's been a real treat to listen to your talk, and we've got a small thank you for the presentation tonight.
Yep.
It comes in a gorgeous little box there. I've no idea what might be inside, but would you join me in thanking Gary for a terrific presentation?
Thank you.
I'd just like to finish up by letting you know about our next Research Tuesdays event. Next month will be something slightly different. It's the finals of our annual 3-minute thesis competition, where 10 of our top PhD students have just 3 minutes each in front of a panel of judges to explain their research and its significance. It's always a lot of fun. I hope to see you back here in the Braggs Lecture Theatre on Tuesday the 9th of September for our 3-minute thesis finals. It'll start a little later than normal at 6 p.m. Thank you again for coming, and good night.